Okay, node voltage. I've heard it also called node voltage analysis. However, that's too many syllables. The node voltage method, or the node voltage systematic method, or just plain old node voltage. I've been very excited and looking forward to recording a lecture about node voltage for a very long time. And now I'm finally doing it. If you there's some, this is just a matter of opinion. It doesn't reflect too much on your character how you feel about this, but you could argue that if you could only know one thing in your life about electrical engineering, or if you were to take some sort of course in elementary circuits and only remembered one thing from that course, it would be how to perform node voltage. If there is one thing that brings you from knowing nothing about circuits whatsoever, nothing about electrical engineering whatsoever, nothing about voltage or current whatsoever, to knowing something, to be able to understand, maybe there's a chance you understand something about what somebody's talking about when they talk about circuits, you learn how to perform node voltage. So this is extremely important. If you watch this and you don't understand it, I don't care what you do for a living. I don't care if you work in a textile mill. I don't know if anybody does that in the United States anymore. Write novels, play professional violin, whatever else people do that's not engineering. There is no other jobs besides being an engineer. I don't know what that is. Anyway, if you don't understand this, you watch this and go, I don't know what he's talking about. Well, first of all, watch basic circuits, but if you still don't know what I'm talking about, find somebody else who's lecturing about node voltage. And maybe they'll explain it better than me. In fact, it's very likely they do, because my head tends to be in the clouds often. Right? And figure out how to do node voltage. You probably will never use it in your life ever. But you also will never use Algebra 1. So, it might come in handy, you will never know. So, before I go into it, I'm going to put some prerequisites. I made a whole video lecture of prerequisites. The problem is that I don't want this to depend on that too much. So, the first one, node voltage, I won't go into the semantics of Ohm's law, not node voltage. Ohm's law, semantics of saying what Ohm's law is so much. For the purposes of this lecture, when I say Ohm's law, all I mean is the equation voltage is equal to current times resistance. You may perform Ohm's law, or apply this equation, that is, when and only when your current is defined according to voltage drop. So if this has a resistance of 2 ohms, and it has a voltage across it of 2 volts, then the current that defines goes from the plus terminal to the minus terminal. So 2 volts is equal to this current, which you don't know, times 2 ohms, which means that the current is equal to 1 amp. If I were to draw the exact same thing, I say this were 2 ohms, and this were 2 volts, and I want to ask you, what is this current? And I have to specify an arrow. I can't just say, what is the current going through this resistor? Then the answer would be, well, my current's not following voltage drop. Let me define a current that is following voltage drop. That current is 1 amp. The current going the other way must be defined as the negative. So this current would equal minus 1 amp. And for clarity, I'm going to erase this. Okay. So you can only apply V equals IR to find the current or the voltage, where the way that your current and voltage are defined is such that the current goes from the plus to the minus. If you have it not that way, it's just a negative, right? Secondly, in the course of solving a circuit, you'll define many voltages and many currents in order to use relationships like Ohm's law. You could redefine them over and over again however you like, right? They don't fix how you define the voltage across that component. What matters is that when you apply Kirchhoff's voltage law and Kirchhoff's current law, how you define them is consistent with the law you're using around the loop or node you're using. So, say I have two loops. And I say, okay, I'll add more components in here. I don't care about making this neat. I want to use Kirchhoff's voltage law around this loop. To apply Kirchhoff's voltage law, I have to define voltages such that they are aligned with each other. That is, here's an example of that. If I were to draw several currents going from the plus terminal to the minus terminal, so plus 2 minus, plus 2 minus, plus 2 minus, plus 2 minus, all the currents would be going the same direction, in this case counterclockwise around this loop. And I define voltages this way, and the voltages are related by Kirchhoff's voltage law when they're drawn this way, that the sum of all of these individual voltages is 0. But I can then go over here and say, okay, I want to define these voltages. And do another Kirchhoff's voltage law. Well, I can do that too. But I just defined a voltage with the opposite polarity as I did over here. So, Kirchhoff's voltage law still applies around this loop as long as the voltages are all oriented the right way with respect to each other. Right? So components don't define polarities. The physical law you are using defines polarities. For some reason, students struggle with this. I don't know why. They'll be like, I did some sort of law, and to do so, I defined a current going this way through a component. Or I defined a voltage this way across a component. And then when I go to another node or another loop, and I do another physical law, they want to define it the same way. And it's like, you don't have to do that. It's the physical law you're using that determines how it's defined. You could redefine voltage across components all the time. Now, it will turn out, of course, that this voltage is the negative of that voltage. Right? So you switch the sign. Okay. I don't know if that made sense to anybody, but that's something that students get confused with, and that's the only thing I know what to say when that happens. Okay, so now we got those things out of the way. I need to now go into the meat of what node voltage is. So imagine that I were to define several voltages around this loop such that Kirchhoff's voltage law applied. So I'm going to make it so that if I were to draw a current from the plus to the minus, they would all go around a loop in the same direction. So I already did a fairly bad job at drawing this, so let me start over. So minus plus, minus plus, minus plus. I'm just making sure that I erased that little piece right there. My polarities hug these components, otherwise there'll be confusion. So if I were to draw arrows from the plus to the minus, I'm not going to do it because that will clutter up my diagram. But if I were to do so, they would all point this way, right? They would go around this loop this way. Now, according to Kirchhoff's voltage law, the sum of all of these voltages around this closed loop is 0, right? So that would mean that the sum of the voltages from here to here plus the sum of the voltages from here to here equals 0. So I'll call this one V1, call this one V2, call this one V3, call this one V4, call this one V5, call this one V6, call this one V7, call this one V8. And then the sum from I equals 1 to 8 of VI is equal to 0. Wow, that's a really bad 0. Well, so I can move things to the other side, right? So I can do the sum for I equals 1 to 4 of VI is equal to minus the sum from I equals 5 to 8 of VI. And for some reason, I drew a backwards 8 up there. I've now exposed myself as somebody who draws infinity way more often than draws 8. So I automatically draw the infinity instead of the 8. Right? Okay. But what now? I have a minus sign. How do I get rid of that minus sign? Well, I can just switch the polarities of all these. And I can call these new polarities, I don't know, V8 prime, V7 prime, something like that. I mean, they're not derivatives, but where V8 prime is minus V8, V7 prime is minus V7, and so on. And then the sum of the voltages from I equals 1 to 4, Vi, is equal to the sum of the voltages where I equals 5 to 8 of Vi prime. And this would be true by Kirchhoff's voltage law for all possible paths from here to here. I'll call this, so all paths will pass from there to there, no matter which set of components I sum over. If I sum from here to here, zigzaggy like this, or like this, the red ones, if I line up all my voltages so it goes minus plus, minus plus, minus plus, minus plus, or minus plus, minus plus, minus plus, minus plus, because of Kirchhoff's voltage law, they will always sum to the same thing, right? This will always be true. All the sums will be the same. So because of Kirchhoff's voltage law, it doesn't matter what path you take from one node. A node is just an interconnect. This is a node, this is a node, that's a node, that's a node. You'll always get the same voltage. And this means that it is not only valid to define voltages across components, but also valid in arbitrary networks to define voltages between any two nodes. Okay? This is a very similar concept to if you have a field with zero curl, then we say that represents a conservative force, which means that no matter what path I take, if I do a line integral along that path, if all I pass in at the same two common points, that line integral will evaluate to the same thing, right? So like, say a gravitational field has no curl, then if I integrate from one point to another, the work done, that is force dot dl, along that path from one point to another in a gravitational field, the amount of work done no matter what path I take, if I start at the same place and end at the same place, will be the same, right? Same idea, completely the same idea. And if you were to go in a closed loop, because the curl is 0, then a line integral around a closed loop is 0, because the line integral of a closed loop is equal to the surface integral of the curl inside the loop, and that's all 0. Okay, Green's theorem, Stokes' theorem, blah, blah, blah. And that's actually where Kirchhoff's voltage law comes from, right? It comes from the curl of E is equal to the change in time of magnetic field. And if we assume that's 0, sometimes criminally we assume that's 0, then the sum of the voltages around a closed loop is 0. So now we could define voltages all across all over the place between any two nodes, which allows us to do something that's also analogous to potential energy. I'm going to take a sip of water. Okay. We can define a node as 0 volts. Now that may not make so much sense at first, because a voltage is always across. You need two nodes to make a voltage. So how could you make a voltage at a node? Just one node. Well, you make it such that it is the difference between two nodes. It's the difference between that node and some other node. And how we know whatever that node is it's labeled. And it's labeled with a special symbol we call the ground. So because we can define voltages across between any two nodes in a circuit, I can say that the voltage here And I have all these voltages written on here, which is kind of annoying because now I don't want to write component voltages, I want to write node voltages. So now I'm just going to erase all of them. I could use letters and numbers, but then that would just still get confusing. I just want to make sure there's only one type of voltage on the circuit at a time. Okay, if I take this and I call it VA, say it's equal to 5 volts, that doesn't mean, that means it's 5 volts between here and here, where it has a plus and that has a minus. So node voltage is a voltage which is defined with respect to a node called ground. You always know what it is because it's marked with the specific symbol that looks like a ground. This seems analogous to the idea in freshman physics where you have potential energy, and you always say that the ground is 0 potential energy, or altitude 0. But we always do that for convenience. You would get the same physics if you defined any other altitude as 0 potential energy, and defined, it's just convenient, right? You could think of this as analogous to that. It wouldn't be completely wrong. The reason why we call it ground, though, is not exactly because it's analogous to the idea of potential energy and how it's convenient to define the ground as 0 potential. It's that how the power grid works, how that transmission works is the ground is actually used like a ground plane, which is somewhat of a advanced concept for this lecture, so I'd get it kind of ahead by saying that. What that means is, well, your outlet is plus or minus 120 volts RMS. Another advanced concept is beyond this lecture. The power transmission system actually transforms it up way beyond 120 volts because then you have less current on the line, it's more efficient. If you wanted to get that voltage out, what you would do, what that means, that's like just a wire, right? Like, what does it mean to have these kilovolts on just a wire strung up between towers? What does that mean? Well, if you were to drive a big metal pole into the ground, right, and then connect yourself between that transmission line and that metal pole that's pounded into the ground, then you would then get electrocuted. So when you build a new building and you're supplying electricity to it, one terminal comes from the line. There's only one wire though. There isn't two. Where's the other one? The other one is an image underneath the ground. 0 is between. It's actually like differential mode between it and the image to get that voltage out. The other terminal you want to be the ground. The literal ground. So, if you got lost in there, that's okay. I'm just trying to say why it's called ground. It has to do with the concept of pounding a pole into the ground as the opposite terminal. But, so I could define voltage with respect to the ground. Okay, so what does that do? How does that change how I define my voltages across components? Well, like what's the voltage across this, for example? Say this were called VB. This node, voltage at just that node, not across any component, just at that node is VB. Well, I have a voltage from ground to VB, like I could define a closed loop. Let me get out another color. So, ground to VB, and then I have to line up my voltages. I could define another voltage across this component, minus plus, and then to do Kirchhoff's voltage law, this needs to line up again, so minus plus. So minus plus, minus plus, minus plus. So what's this voltage minus plus? Well, it's how far VB is above the ground. So that's just VB. So VB. The voltage here, minus plus, is the voltage we're interested in, right? So, I don't know, I'll take my pink and I'll say V comp. The voltage across this component, the thing of interest, right? I want this plus here and this minus here, this thingy. This box right here. So plus V comp for V component plus What's this voltage? Well, if there were a minus here and a plus here, it would be VA. But it's backwards. There's a minus here and a plus down here at the ground. So it's minus VA. So minus VA equals 0. So V comp, if I move everything to the other side, is VA minus VB. So the voltages we all know and love, the voltages across individual components, are just differences of node voltages. Specifically, the difference between the voltage on one side and the other. And it's really easy to remember which way the difference goes, because it's the voltage at the plus minus the voltage at the minus. So it's plus VA minus VB. Plus VA minus VB, right? Cool. So now we know what node voltages are. We have the concept of ground, right? So how is this useful for solving circuits? How is this useful for finding individual voltages and currents through circuits? And how is this better than just doing Kirchhoff's current law and Kirchhoff's voltage law, like how I did poorly and sloppily, but maybe correctly? I had to correct myself twice in my basic circuits lecture. Well, the best way to explain that is with a bunch of example problems. But I'll write down the steps here, just so there's like somewhere in this the steps are written down. So step 1, write Kirchhoff's current law. KCL stands for Kirchhoff's current law. You never see it written out. At all but one of the nodes. Okay. So, what do you mean all but one? Do you get to choose which one you don't? Well, in a nice world you would. But you see, with engineering, there's some weird sort of rules. Like, things people came up with because they wanted to feel important. Or they just wanted everybody to do it exactly the same way. One of those is, you don't do Kirchhoff's current law at the ground node. And you'll find that circuit diagrams have a tendency to be written in ways that suggest that they don't think you're ever going to do that, right? Oftentimes, the ground node is not written like all the wires coming together and then there's a ground there. It'll just take that off, and then they'll just have like several grounds all throughout the circuit. And it's implied that if you see a ground symbol, it's connected to all the other ground symbols by it being ground, right? So you have to draw fewer lines on the circuit. Which means if you have to do Kirchhoff's current law at the ground, you can still do it, but you have to find all the grounds. And then they'll draw independent voltage sources, where they don't put a source between ground and that voltage. So if you were to do, they just draw a voltage there. So if you were to try to do Kirchhoff's current law at the ground, you actually have to include all the voltages, all the sources as well. And then you'll have things like op-amps, which have power supplies to them. And those power supplies are independent voltage sources that are connected to ground. So then, if you wanted to do Kirchhoff's current law at ground, you'd have to remember that and make sure to include current coming out of an op-amp. You can still do it. Nothing prevents you from doing Kirchhoff's current law at ground. Despite how much they try by drawing circuit diagrams that may obscure ground, you can still do it. But they're written in such a way that assumes you won't try, right? And it's easy to, if you do, and you don't know what you're doing, confuse yourself. So, that is all but ground. But you write them in terms of node voltages. But I said use Kirchhoff's current law. But I said write in terms of node voltages. Yes, that means that your writing of the Kirchhoff's current law is going to apply Ohm's law over and over again. Right? Because you're going to be writing your currents in terms of voltages, so you just use Ohm's law. So that'll be a round of resistors in the denominator. 2. Solve the equations. Solve the KCL equations for the node voltages. Writing is hard. 3. Use node voltages to find what you want to find. And oftentimes in academia, the problem is with just having the node voltages. But usually, you want the node voltages for a reason. You want to find a current or something. You will always have to solve a linear equation of with the amount of unknowns being the amount of nodes in the circuit minus 1. And that's where the torture begins, right? So let's go through the example problems. So I don't remember what exactly is in here. Let's see what they are. Okay, first one is, okay, this. Sweet. So the simplest case is always when you have just resistors and independent current sources. So we'll build up from there. First step, which I didn't list on my list of steps in the previous page, but I mean, gee whiz, pick a ground. Well, this circuit has 3 nodes in it, I can see, right? I'll call them 3 nodes. This is a node, that's a node, and this is a node. A node is any just interconnect of wires with no components between it. So all of this, from here, all the way over here, here, and here is all a node, right? All of this is a node. All of this is a node. There are 3 nodes, right? Pressing the undo button over and over again. Okay. So I'm going to pick the one as the ground, the one with most interconnects to it, because that would be the most inconvenient to write a Kirchhoff's current law at, right? So I'm just going to pick the one at the bottom. This is really common. You pick as your ground the one that's just lowest down in the way the circuit diagram is drawn. Nothing scientific about that. It's just, natural reaction. You think ground is like the low part, just like the top of the page and the bottom of the page somehow means something. And then we'll call this one V1, and we'll call this node voltage V2. You have to name your node voltages things. Then we write Kirchhoff's current law at V1 and at V2. So let's start by writing Kirchhoff's current law at V1. Now it doesn't matter if you sum all the voltages going into a node, or you sum all the voltages coming out of a node. As long as you do it consistently, you'll be good. I always sum all the currents coming out of the node. So our first current goes this way. How much is it? -4. And I can put units on these equations. It's -4 amps because the opposite direction of this independent current source sourcing 4 amps. Plus the current going this way, which is V1. I use Ohm's law. Current should follow voltage drop to do Ohm's law. So I define my voltage so my current is going from the plus to the minus. This voltage is V1 minus the ground. Remember, the ground is 0 volts. Divided by the resistance, which is 2 ohms. And last but not least, I don't know what that expression has. I'd actually say that, but there's nothing that would suggest leastness here. The current going this way, which is this voltage, divided by this resistance, which is V1 minus V2. Remember, it's voltage at the plus side minus node voltage at the minus side, divided by the resistance, which is 1 ohm. And then the sum of all the currents going out of the node equals 0. So I can clean this up a little bit. 3 halves V1 minus V2 is equal to 4. Hopefully I didn't make a dumb mistake in there. Okay, do my next Kirchhoff's current law. So that one is at V2. So first I have this current going here, which is defined by this independent current source as being 4 amps. I have this current going here, which is V2 minus the ground divided by 1 ohm. This should be a plus. I don't know why I put an equals there. This should be a plus. I'm summing these currents. Plus the current going here, which is, here's where students get confused. You have to redefine it. It's okay to redefine it. The signs work out. Plus, minus, V2 minus V1, this should be a plus. I don't know why I keep writing equals when this should be pluses, over 1 ohm equals 0. If you I highly recommend you always sum up currents going out or currents going in. Since I am always summing currents going out, in all these terms, I always see the node I'm on first. So in my V1 equation, I see V1 minus something plus V1 minus something, right? It's always V1 minus something else over a resistance. The node I'm on minus another node over resistance. When I node V2, it's V2 minus something else over resistance. V2 minus something else over resistance. V2 always comes first. And because I'm just applying Kirchhoff's current law at that node, it's physically valid. Doesn't matter if I define something the opposite as I did in the previous equation. Doesn't matter that these are switched. So I can clean this up too. 2v2 minus v1 is equal to minus 4. What do I want to say about this? Nothing really. I'll just solve it. I first tried looking for an easy elimination, and I seem to have found an easy elimination so I'll go for that. So 3v1 minus 2v2 plus is equal to 8. So I just took this equation, put it down here, and multiplied both sides by 2. Right? Now I have 2v2 here, so I can cancel that, and so I get 2v1 is equal to 4, which implies that v1 is equal to 2 volts. I plug that in here, I get 3 minus v2 is 4, so v2 is equal to minus 1 volt. If you have time, which on some exams you don't, so if this were a test, then you would write those down, you would go on to the next question. Once you were done with the whole entire rest of the test, come back and check if these are right. It's really easy to do so, just plug them into these equations. You can also draw on the circuit if you like. But I generated this from the top equation, so the top equation is automatically going to check unless I made a really dumb mistake. So the bottom equation, let's see here, minus 4, wow, 2 plus 6 is 8, so it checks. So these should be the right answers. V1 is 2 volts, and V2 is minus 1 volt. It's okay to have voltages less than ground. It's relative. Like you could define, when you do kinematics in freshman physics, you can always have things go underground. You can always have a pit. That's perfectly fine. Okay. When it comes to independent voltage sources, there's some intuition you can get about things like that. But when there's only independent current sources, just whatever. Like, voltages can be whatever. Okay, next example problem. What am I seeing? Oh, seeing this. Well, okay, so this problem looks like one of those where I just write down the node voltages, and I don't bother solving them. I don't have actual numbers here. I just have, like, abstract currents and voltages. So I'll just write down the node voltages for this circuit. Again, first I gotta pick a ground. I'm gonna pick as my ground this node because has a lot of things connected to it, and it's kind of towards the bottom of the circuit, I guess. And then I'm gonna do Kirchhoff's current law here, V1, which the extent of V1 is like this entire thing. Okay, and then V2 over here, which is like this entire thing. And then V3 over here, right? So I only have 3 equations and 3 unknowns. I'm not going to solve them. I'm just going to write down my 3 equations with my 3 unknowns in them. So my Kirchhoff's current law here is V1 minus ground. I'm going to stop writing the minus grounds, divided by R1 minus IA, because IA is coming in, and I'm summing the currents going out. I always do that. I will always do that in this lecture. I won't ever change it up. Plus V1 over R2. You could start by combining R1 and R2 in parallel to simplify the circuit before you start solving. I'm not going to do that, but you could if you wanted to. They are in parallel because they connect the same 2 nodes. It doesn't matter if there's something in between here. The circuit is exactly the same. when any of the things that connect the same two nodes connect the same two nodes. So if I see a bunch of things in parallel like this, current resistor, current source resistor, I can change the order of them as long as they connect the same two nodes however I like to. So, and then I have V1 minus V2 over R5. And then lastly, minus IB. And these should all sum to 0. We're assuming we're given IA and IB. And we're given the resistances, and then we're not given the node voltages. Then so I'll call that 1, 1. Then I do Kirchhoff's current law at node number 2. So that's, oh dear, this gets tiring after a while. V2 over R3 plus V2 minus V1 over R5 plus V2 minus V3 over R4. I think I got all the resistors. Plus IB minus IC. And these all sum to 0. Right? Remember, IB is coming out, IC is coming in. And then I write a third one for no V3. Let's see, did I get them all? 1, 2, 3 resistors and 2 sources. Yeah, I hope so. V3 over R6 plus V3 minus V2 over R4 plus IC equals 0. And those are my 3 equations and 3 unknowns, and I could solve them symbolically in terms of the 3 currents and the 6 resistances, but I won't because that's a total pain in the butt. But you could. Okay. Oh, well, I wonder if weird swallowing sounds would get in the video. Next example problem. So first I pick a ground. I'll just pick this one because why else? I mean, I'm not the most picky about my ground picking. And then, so that's my ground. What nodes do I have? Well, I have a node over here. We'll call this V1. I have a node over here, I'll call it V2, a node in the middle here, and I have a node on the right side here, I'll call it V3. And I believe with that I got them all. So, now I write Kirchhoff's current law at each of those 3 nodes. So, V1 over 1 ohm plus V1 minus V2 over 4 ohms plus 2 equals 0. And I'll call that 1, 1. And then number 2, I'll just write all the node equations first. So they all end up in the same place before doing simplification. So at number 2, we have V2 minus V1 over 4 plus V2 minus V3 over 2 minus 1 equals 0. And then at node 3, I have V3 minus V2 over 2 plus V3 over 3 minus 2 equals 0. Okay, so then I'll try to clean these up a little bit. Multiply for number 1. I'll multiply both sides by 4, so that will get me 5V1 minus V2 is equal to minus 2. For number 2, yeah, again, I'll multiply both sides by 4, so that gets me 3V2. I'll do the V1s first, so when I try to put these in a matrix, I don't get confused. So multiply both sides by 4, I get minus V1, and then plus 3V2, minus 2V3 is equal to 1. And then for my third equation, I'll get multiply both sides by 6. There's no V1 in this, so that makes minus 3V2 plus 3V3 plus 2V plus 5V3. Ooh, mistakes. This needs to be a 4. Yeah. Ooh. Do so much stuff in my head that, like, inevitably I'm just gonna pooch something real bad. So, equal to 12. Let me double check all this. So, multiplying both sides by 4. Up, that means this needs to be a minus 8. I forget to like multiply the current sources by 4. It's a problem. Okay. Multiply both sides by 4, I get 4v1 plus 1v1, which is 5v1, minus 1v2 is equal to minus 8. Multiply both sides by 4, I get v2 plus 2v2 is 3v2, minus v1 is minus v1, minus 2v3, because I'm multiplying both sides by 4, is equal to 4. I have to multiply the 1 by the 4. Okay. Multiply both sides by 6, they get 3v3 plus 2v3, which is 5v3. Minus 3v1, I mean v2, sorry, there's no v1 in this one, and then multiply the 2 by 6 to get plus 12 on the other side. Okay, now, this is very mainstream and not very popular, but my favorite way to solve 3 by 3s, well, is use MATLAB. But if I don't have MATLAB, then use Python. But, and if not doing that, use a TI, like a Texas Instruments graphic calculator, which usually you could do, but if you have like a stringent professor who doesn't let you use any sort of calculators on a circuits test, which happens quite a bit actually, then you gotta do this by hand somehow. So, yeah. Okay, so I'm gonna write my first matrix, called D. 5, minus 1, 0. I just write just the coefficients into a matrix. Minus 1, 3, minus 3. That's all the coefficients of V2. And all the coefficients of V3, 0, minus 2, 5. And I just take the determinant. So I find a row or column with a 0 in it. This one, the top row is fine. So 5 times the determinant of the minor, which is 15, minus 6, which is 9. So there's a trick for doing determinants of 3 by 3s, but I always found that doing expansion by minors is just faster than using the trick, than doing the diagonals. So this is in a weird position. So I do plus minus minus 1, which is positive 1, times the determinant of the minor, which is minus 5, minus 0. So it's just minus 5. So this is equal to 45 minus 5, which is 40. Wow, that's a big number. Okay. Sweet. 15 minus 6 is 9. Okay. Then I do I call it dx, but it's the matrix representing V1. Is these currents on the right side here replacing the column for V1. So it's the same as the D matrix, but it's going to be 8, 4, 12 instead of 5, minus 1, 0. And then everything else is the same. I do a determinant. So that's going to be 8 times this minor, which is the same as before. So that's 8 times 9. I can check it. It's 15 minus 6. Plus 1 times the determinant of this times this minor, which is 20 minus 24, which is 20 plus 24, which is 44. So this is equal to 72 plus 44, which is 116. I hope that's right. I'm not using a calculator or anything. Okay, so I call this dy, but it represents V2. So 5 minus 1, 0, 8, 4, 12, 0, minus 2, 5. Okay, take another determinant. This is 5 times 20 minus 12 minus 24. So okay, 44 again. Yeah, that works out. Minus 8 times this minor, which is minus 5 minus 0, so it's just minus 5. So this is 220 plus 40, which is equal to 260. And lastly, I call it DZ, but it's like the V3 matrix is the same as the top matrix. except I put the 8, 4, 12 in the right slot. Now I want to take advantage of the 0, so I'm just going to go down these. I'm going to go down the column instead of across the row. So it starts out the same. 5 times this determinant, which is 36, minus 12, which is plus 12, so 48. Minus 1, which is plus 1, times the determinant of this minor, which is minus 12, minus 3 times 8 is 24, right? So plus 20, minus 12 plus 24, which is positive 12. And this is equal to 240 plus 12, which is 252. Okay. The chances of making a stupid mistake somewhere in here are near certain. It's like 99.9999 chance of failure. So this will give me V1 is equal to 40 over 116, which is equal to 10 over 29. Oh dear. V2 is equal to, I got that upside down, didn't I? It's 29 over 40. I don't know what got into me there. You divide by D. Okay. I can't remember how to do Kramer's rule correctly. So 116 over 40, which is equal to 29 over 10. So 2.9. Okay, V2 is 26 over 40, 260 over 40, which is equal to 13 over 2. So if you like decimals, I don't. This is 2.9. This is 6.5. And then V3 is equal to 252 over 40, which is equal to, 240 is 60, 12, 63 tenths, 63 over 10, which you could say is 6.3. Let's see here. Is that 63? Yeah. Now, we want to check this. Always, it's like, thanks for doing my circuits homework with me. So we want to make sure they check. So, checks. 5 times 29 tenths minus 13 halves is equal to minus 8. Okay? So, 29 halves minus 13 halves is equal to 16 halves. Oh no. Positive 8. You know why? Because I didn't get minus 8 in the determinants. Yeah, that's correct for what I solved. I didn't solve the right thing. Now I have to do this all over again. And yes, you have to. This will be in the recording. This is why you always check your work. So, what does that change? Well, first of all, it makes this a minus 8. That's about it for that one, right? And this makes this a plus 8. That's about it for that one. But for this one, there's a minor that's changed. So I have positive 1 times minus 12 minus plus 24. So that's minus 12 minus 24 more. So that's minus 36. So instead of 12, it's minus 36. Okay. That's okay, cool. And that will change these answers. So this is not 116. This is minus 72 plus 44, which now I have to do a subtraction. Minus 72 plus 42 is 30, so plus 44 is 28, so minus 28. 5 times 44 is 220, minus 40 is 180. And then it's a fate 180, but oh well. This is 240 minus 36 is 204. I don't know, did my pin size shrink? Yes, okay. Fix that. Well, okay. So that changes our answers for all the voltages. Okay, so V1 is minus 28 over 40, which is minus 7 over 10. V2 is 180 over 40, which is 9 halves. And V3 is 204 over 40, which is 51 over 10. Okay, let's check that now. So 5 times minus 7 tenths minus 9, so yeah, that checks. So redoing the checks, um, 5 times minus 7 tenths minus 9 halves is equal to minus 7 halves minus 9 halves, which is equal to minus 16 halves, which is equal to minus 8. So the first one checked. Good. Next equation. Plus 7 tenths plus 27 halves minus 51 fifths is equal to, well, I make these all tenths, right? So 7 tenths plus 135 tenths minus 102 tenths. Oh, it should be 40 tenths, right? Yeah, it's 40 tenths, so that checks. One more to go. Okay, so minus 27 halves plus 51 halves is equal to 24 halves, which is equal to 12. Yes! Okay. And so, for the box around it, I got my no voltages. Thank you for going on this journey with me. That is, as long as these equations are correct. Which I could have made a mistake during this step. Or made a mistake writing them. And this is going to have comments. So you may let me know in the comments whether or not there was a mistake early on. But at least once I got to this step, I solved them correctly. I managed to get them correctly after that. Okay, next example problem. Ooh, something a little less complicated. First we pick our ground. Oh, well. We see something here that we have not seen before. That is an independent voltage source. How do you do node voltage when you have an independent voltage source in your circuit? Well, there's two things you can do. The first thing is the simplest and what I will demonstrate here. And that is, you can use the independent voltage source to define a node voltage. So say I make this the ground. Then, by definition of this independent voltage source, this voltage is Vs. So the voltage at this node, relative to the ground, is just Vs. Which would assume would be given, because usually these problems, the resistances, the voltages and currents, the resistances and the sources are given, the node voltages are what you need to find. So that voltage source would be given, I find Vs. That gives me what Vs is, automatically, if I define the other end as the ground. So now, I only have one more node voltage left to find. And that is this one, which I'll call V1. And so I can write a Kirchhoff's current law at V1, V1 minus Vs. Remember, Vs would be something that would be given. This may be more clear if I actually have like numbers on this. Excuse me. V1 minus Vs over R2 plus V1 minus ground over R3 minus I source is equal to 0. And then I just solve this for V1. Right, so then V1 is V source over R2 plus I source divided by 1 over R2 plus 1 over R3. Now, you might be wondering, what about R1? Doesn't it do something? And my answer is, yes, it does something. It makes it so that Vs has to pump out way more current. That independent voltage source has to pump out current that flows through this resistor, right? You have a voltage here of Vs, and so you have a current here of Vs over R1. But the independent voltage source is an independent voltage source. It always succeeds in doing so. It always succeeds in maintaining the voltage it's trying to maintain. So it doesn't affect the node voltages in any way. So the node voltages are going to be the same whether R1 is there or R1 isn't open or whatever value R1 has. It just puts like a strain on the voltage source if you want to think of it that way. Next example problem. Now I have a dependent source. What do I do here? Well, same as you'd always do. We want to pick our ground. What should we pick as our ground? Well, we could pick, this is a weird choice, but I'll try to explain this. So, we could pick this as our ground. But then, the node we pick as ground will not be the node connected to this voltage source. It's not independent anymore, it's dependent. It's dependent on the voltage defined here, called Vx. That x looks like a lambda. I don't want to switch back to brown to fix it. It's an x, not a lambda. We could put that it's not touching this voltage source. So then we have to use a technique which I haven't explained yet called super node. Okay, we don't like that. What if we put the ground, so let's not put the ground there. What if we put the ground here? Well, I don't like that either because that's not connected to very many other things. So that produces more complicated Kirchhoff's current laws than necessary. So I don't like that. So I'm going to put my ground actually at the top of the circuit. I'm going to put my ground here. So it's connected to 3 other components, but it's actually it's on one side of this dependent voltage source. That's the most convenient placement for the ground I can see. So now let's do Kirchhoff's current law at the one remaining node. So this node here, its voltage is minus 4 Vx. I accidentally color picked the paper. So minus 4 Vx, because this right here is the negative of this, which of the voltage that the voltage source is defining. So I get a negative of whatever it's defined as. That actually doesn't solve anything because I don't know what Vx is. So if I called this node here V2 and called this one down here V1, I have this node equation left that says that V2 is equal to minus 4 Vx. But remember when we do node voltages, we want to write all of our Kirchhoff's current laws in terms of node voltages. Well, this isn't a Kirchhoff's current law. It's not a Kirchhoff's current law, but we still want to write this node equation. It's still a node equation in terms of node voltages. So we want to write Vx in terms of node voltages. Well, as it turns out here, you see Vx is equal to V1. So instead of writing V2 is equal to minus 4 Vx, you want to write V2 is equal to minus 4 V1. Because it's connecting V1 and ground, right? So that's one of our equations. The other equation is Kirchhoff's current law if you want, which I previously mentioned and haven't done yet. So that would be 3 plus V1 over 4 plus V1 minus 4Vx divided by 10. Well, Vx is equal to V1. So this is 3 plus V1 over 4 plus 5V1 divided by 10 is equal to 0. So 3 plus 3/4 of a V1 is equal to 0. So divide the 3's out. V1 is equal to minus 4. And if V1 is equal to minus 4, V2 is equal to 16. Now let's look at the circuit and see if that makes any sense. So this is 16, say this is 16 volts here. That would mean that Vx had to be minus 4 volts. So this right here is minus 4 volts. So this right here is minus 1 amp. V1 equals minus 4 volts. So this voltage drop here is 20 volts. So this current here is 2 amps. So I have minus 1 amp coming down this way. Let me check. Let's see. Did I do this right? So this is 16 volts. Oh, yeah, this is 16 volts, which means but that's opposite of this polarity, right? So that means that Vx is minus 4 volts, but Vx is defined this way, so this is minus 4 volts. Even I mess up passive conventions sometimes. So this right here is minus 1 amp, which means that going the other way, it's 1 amp. So I have 1 amp coming in here, 2 amps coming in here, so 1 amp coming down there, 2 amps coming in here makes 3 amps coming out there, which makes sense. So that's enough checks. So, I floundered through that, but these should be the right answers. It's real easy to make stupid mistakes doing this. Next example problem! This one, the nodes are already labeled. Let's see, we have... And the ground is already picked for me. So I have 5 nodes. Okay. Well, I am definitely not going to solve a 5x5 and record it. To do a 5, I think the fastest way to do a 5x5 is just plain old Gaussian elimination. But, so if you were looking forward to seeing me do that, well, good. Well, I disappoint you. But that will take several hours. So I'm just going to write the node equations for this, and then leave it to you to solve it, but you won't, and you better not, because it would be a big waste of your time. If you wanted to, just plug it into MATLAB, okay? Just plug these into MATLAB, do a linsolve. If you don't have MATLAB, find a Python package that'll work for you. So, at V1, we have, so number 1, we have V1 minus V5 over 1. Wait, we have to do supernodes. Oh dear, we have to do supernodes. So I have to explain what supernodes are. So the idea behind a supernode is Kirchhoff's current law applies to any bag, right? Not just a node. So I can envelop any part of a circuit in some sort of bubble, and the sum of the currents going in, or the sum of the currents going out of that bubble, would be 0. You end up in this kind of block when you try to do Kirchhoff's current law at nodes with an independent voltage source. Because remember, independent voltage sources tell you nothing, absolutely nothing, about what current is going through them. You cannot assume it's anything. Right, so if I try to do a Kirchhoff's current law at V1, like what I just did, and went, there's a voltage source, and I'm stuck, so what's this current? I don't know, it's a voltage source. I don't know what current is going through a voltage source. So what do I do? Well, I really don't have a choice but to expand how much junk I'm including in my Kirchhoff's current law. So I'll just envelop the whole voltage source in that. And do a Kirchhoff's current law from that, of using that whole bag, including both sides of the current source. And this is what that looks like. So V1 minus V5, this looks like Vs, but it's a V5, divided by 1, plus V1 minus V3 divided by 5, and I got these two pathways. Then I have to do this one, plus V2 minus V4 over 4, plus, I'll call this 1-2, plus V2 minus V3 over 10 equals 0. So that's this current plus that current plus that current plus that current equals 0. But I now took two nodes and I wrote only one equation. But I need as many equations as I have nodes. So where's my second equation? Well, it's this. That is, V1 minus V2 is equal to 4. It comes from the independent voltage source itself. So there's my two. So I get, every time I have a supernode, I get two equations. One Kirchhoff's current law and one that just relates the two nodes based on what the independent voltage source is. Okay. Now here we have to do another supernode. So we'll do another supernode. So first we do, I'll call this 3-4. So first we do the Kirchhoff's current law. That is V3 over 8 plus V3 minus V2 over 10 plus V3 minus V1 over 5. Let's see, that's going to pass, right? That one, and that one. Good. Is equal to plus V4 minus V5 over 1 plus V4. I hate it when I accidentally color pick the paper. V4 minus V2 over 4 minus 1, because I have this current source here, equals 0. And then I have the equation that comes from the source itself, which is V4 minus V3 is equal to 8. So those are my equations for nodes 1, 2, 3, and 4. I have one left, and that's V5. But that one, again, my ground is here, and it's defined a voltage source between it and ground. So V5 is equal to, well, just 4Ix. But what is Ix? I need to write that in terms of node voltages. Well, that's this current. Well, what's that current? Well, it's the sum of that current and that current, right? You can do a little Kirchhoff's current law here. So Ix is V2 minus V3 over 10 plus V1 minus V3 over 5. So that's our last equation. And so our equations, that is all 5 equations. Here's the first one, this Kirchhoff's current law, this independent voltage source, this Kirchhoff's current law, this independent voltage source, and this dependent voltage source, where I had to do a little trick right here to find this current in terms of node voltages, right? I just summed this current and that current together to get that current, right? And that's 5 equations and 5 unknowns, and now you can solve it. Good luck. Usually professors are nice, and they don't give you things on non-calculator tests that are more than 3x3, and things on calculator tests that are more than 4x4. But if you get a 5x5, that's just that. Yeah, life. Anyway, next example problem. It's kind of my fault because I put that in there. Okay, this is what. So I mentioned in some previous lecture that you can combine resistors in parallel to get an equivalent resistance. You can combine resistors in series to get an equivalent resistance. But what if you had something like this? We can't combine resistors to get an equivalent resistance that easily, right? It's like there's no parallel here. The two resistors that kind of look in parallel, they have one resistor in between. There's also no series here, right? All the nodes have at least 3 things connected, so I can't have anything in series. So can I find an equivalent resistance of this? And the answer is yes, you can. Use node voltage. So let's do that using node voltage. So I'll call this node V1, call that one V2. This one is Vs. So I write down my node equations. So the one at V1 is V1 minus V source divided by R1 plus V1 minus ground over R3 plus V1 minus V2 over RB for like R bridge. It's not a 13, it's a B. Equals 0. And then I have a node equation here. V2 minus Vs over R2 plus V2 over R4 plus V2 minus V1 over R bridge equals 0. Okay, so 2 node voltages. I have 2 equations and 2 unknowns. Vs is a given, so I can solve. But this is going to be brutal. So, V1, 1 over R1 plus 1 over R3 plus 1 over R bridge minus V2 times 1 over R bridge is equal to Vs over R1. Hopefully I didn't mess up there. V2 times 1 over R1, R2 plus 1 over R4 plus 1 over R bridge minus V1 times 1 over R bridge is equal to Vs divided by R2. Okay. So I should see some symmetry and interchange between 1 and 2 and 3 and 4. I don't really see that yet, but no, I kind of do. Yeah, I do. Let's just keep going with this. So, let's try inverting the matrix. So the determinant is that minus that, which is 1 over RB times, this is with a minus sign, 1 over R1 plus 1 over R3 plus 1 over RB plus, oh, these are reversed, right? Okay, so for reference, so I don't make a dumb mistake, I gotta write this matrix first, because I was about to really mess that up. So the coefficients of V1 are 1 over R1 plus 1 over R3 plus 1 over R bridge, and then it's minus 1 over R bridge. And the coefficients of V2 are minus 1 over R bridge, and then 1 over R1 plus 1 over R, this is not 1 over R2, this 2 is not a 2, isn't it? R4 plus 1 over R bridge. Okay. So the determinant of that, right, is equal to 1 over R1 plus 1 over R3 plus 1 over R bridge multiplied by 1 over R2 plus 1 over R4 plus 1 over R bridge plus 1 over minus. So it makes a plus because they're both negative, but then it's going the other way, right? You always do plus this way and then minus that way. So, you know what I mean. So it makes another minus. So you get 3 minuses and you get a minus. So minus 1 over R bridge squared. And then I want to do an inverse. You minus these things and you switch the places of these things. So V1, V2 is equal to 1 over the determinant, which is that stuff, multiplied by 1 over R2 plus 1 over R4 plus 1 over R bridge plus 1 over RB plus 1 over RB, 1 over R1 plus 1 over R2 plus 1 over RB, multiplied by 1 over R1 and 1 over R2. So V1 is equal to, let's multiply these two things together, 1 over R1 multiplied by 1 over R2 plus 1 over R4 plus 1 over RB plus 1 over RB R2 divided by 1 over R1 plus 1 over R3 plus 1 over RB multiplied by 1 over R2 plus 1 over R4 plus 1 over RB plus 1 over RB squared, and V2 is equal to 1 over R2 times 1 over R1 plus 1 over R, this is supposed to be a 3, 1 over R3 plus 1 over RB plus 1 over RB R1, all divided by 1 over R1 plus 1 over R3 plus 1 over RB multiplied by 1 over R2 plus 1 over R4 plus 1 over RB plus 1 over RB squared. Yikes. Okay, so then what if you wanted to find the equivalent resistance? Well, that would be V1 over IS is V1. Wait, the V sources are in there, aren't they? Yeah, so this is V source. Man, this is V source. So there's V source in the top. V source in the top. Okay. So, it's got to be proportional to V source. I source is equal to, I can do it down here, right? I can do Kirchhoff's current law here to figure out the current going that way. It's V2 over R4 plus V1 over R3 plus V2 over R4. Which is equal to, and there's VS in the tops of both of these. Gotta just clean up these VS's because they're kind of dirty because I wrote 1. So it's IS is equal to VS times something, right? Okay. That something is 1 over the equivalent resistance because phi is IR. So REQ is equal to 1 over V1 over VS R3 plus V2 over VS R4. Plug these expressions for V1 and V2 in there, and you get your answer. Now, I didn't actually solve this. This is something that I mean, it was a mistake of mine. I didn't actually solve this going in. like beforehand. I didn't prep. So there's this possibility that if you do this, it all simplifies to something all nice and pretty. But why would that matter? Well, it's like do that and you get your answer, but then it turns out the answer is something that I should present because it's all nice and pretty. But I don't know. So that's something for you to look up and see if I plug that V1 and V2 in there, whether or not you get something nice in the end. Well, that's how you do that. Yes, there is an equivalent resistance. You have to do a bunch of algebra and use node voltage, but you can get it. Whew. And if I make a mistake in there and somebody actually watches this, which, like, who's gotten to this point, I'll be let known, inevitably. Okay, next example problem. Let's see, how many more do I have left? A lot. Okay, what's this one? Oh, nice and easy one. Okay, this is 6 volts. This is, I'll call VA. This I'll call VB. VA minus 6 over 20 plus VA minus VB over 5 plus VA over 10 is equal to 0. And then VB is equal to 10 IA, which is equal to 10 times VA over 10, which is equal to VA. Whew. Okay. So, VA minus 6 over 20 plus 0 plus VA over 10 is equal to 0. VA times 1 over 10 plus 1 over 20 is 1/10 of 3 halves, which is 3/20ths, is equal to 6/20ths. Multiply VA is equal to 2. VB is also equal to 2. So let's see if that makes sense. So VB is 2. That means that 10 IA is 2. That means that IA is a fifth, which means VA is also 2. There's no current going this way, so because these two voltages are the same, so I only have a fifth going down. Let's see, and VA is 2 volts, so this is, plus this is 4 volts, so this current right here is 1/5. Yeah, everything checks out. This one was nice and easy. Here are my answers, VA and VB, both equal to 2. Hopefully you understand how I did that. Okay, next example problem. Oh, this is a nice one. Given the node voltages, find resistances, find the power supplied by each source. Time to mix it up a little bit. So, we're given that V2 is equal to 24 fifths. This is not V1, this is volts, comma. Okay, sweet. So, V1 6 volts, 24 fifths. So this current right here is equal to 6 fifths, right? The 6 fifths of an amp. Which means that this current right here is 1/5 of an amp. Just doing Kirchhoff's current law right here, right? So 1/5 comes in, another 1 amp comes in, I get 6/5 going down that way. So I have 1/5 of an amp here. The voltage across R1 is V1 minus V2. So voltage R1, subscript on a subscript, is equal to V1 minus V2, which is equal to 30 fifths minus 24 fifths, which is equal to 6 fifths of a volt. So R1 is equal to so voltage is in the top. So it's always voltage on top. So 6/5 volts divided by 1/5 amps, which is equal to 6 ohms. Okay, and then, so that's 6 ohms. And if this voltage R3 here is minus 2/3 of a volt, that means that this right here is 6 minus 2/3, 18/3, minus 2/3 is 20/3, which means this current here is 20/3 divided by 8, which is 5/6 of an amp. This is 1 amp, which means I have minus a 1/6 amp of an amp going that way. And V3 is minus 2/3. So R2 is equal to V3, which is minus 2/3 of a volt, divided by minus 1/6 of an amp, which is equal to 6 times 2 over 3 ohms, right? Which is equal to 4 ohms. So this one is 4 ohms. Okay. Hopefully I didn't mess any of that up. Right, so I have 6 volts. I have minus 2/3 of a volt, so I have 20/3 across, divided by 8. So it's 4, so that's minus 5/6 going that way. 1 amp gets siphoned off, so I need another like 1/6 of an amp going up. But this is negative, so I end up with a positive resistance of 4 ohms. If you get negative resistances, you usually have made a mistake. So they're positive, so at least sanity checks them that way. So find the power supplied by each source, which means we need to find the current through the voltage source, and we need to find the voltage across the current source. So it's easy to find the current through the voltage source. I just sum these two, the 1/5 going that way, and the 5/6 going that way. Right, so these are supplies, right? So supply, we always want to go anti-passive convention, or go passive convention and flip the sign. I'm going anti-passive convention. P voltage source is equal to 6 volts times the current going this way, which again contrary to passive convention, which would give us power supplied, times the current, which is 1/5 plus 5/6 of an amp, which is 6 times 25/30ths plus 6/30ths, which is 31/30ths, which is 31/5 of 31/5 watts. Okay. Cool. And then find the power, so I got these results so far. Man, I did not work through this before making this lecture. I'm just kind of going, so there's so much fear right now of making a dumb mistake in here somewhere. I just haven't recorded and posted on the internet. Might end up being a joke of some sort. So now I want the voltage across this current source. I want, again, the power supplied. So I want it contrary to passive convention. So I want it so it's going from the minus to the plus. This voltage is V2 minus V3. So power supplied by the current source. That current, which is 1 amp, times V2 minus V3, which is 24/5 plus 2/3, which is equal to, and these are volts, 72/15 plus 10/15 is 82/15 watts. Hopefully I didn't mess that up. 82/15 watts. Okay. And I could check my work by figuring out the power received by the 4 resistors and seeing if the power supplied equals the power received. You know what? Let's do that. Let's keep going. Let's make more work for myself. So, the total power supplied by sources is 31/5 watts, which is 93/15 plus 82/15 watts, which is equal to 175/15 watts, which divide the top and bottom by 5, I get 3, and then the top is 35/5, so 35/5 of a watt. And then power received, I didn't even bother spelling received. I put 2 P's in supplied. I don't know. Like, I did whatever. I don't care about spelling whatsoever. I comes before E except after C, and it is after C, but I don't know if that rule really works. Okay. So 35 thirds. So the power received by all the resistors. So I have that 4 ohm one. That would be 24/5. R2 is 4 ohms, so that's 4/6. Wait, that's a current. What? I'm just. Wow. Don't do that. Don't multiply resistance by current. Multiply voltage by current. Okay. That's 36/5 squared times 4, which is 36/25 times 4. Oh my goodness, this is too much work. You know what? This is so much work, I'm just not going to do it, and hope for the best. Let's just go on to the next example problem. I may have made a dumb mistake in that those power calculations. I'll never know. This is just like a test, right? You just kind of put your answer down, and then you hope it's good, and then you move on with life. Okay, so this is a dumb problem where they already give you the ground to be in a certain place, which is a really dumb place to put a ground. Yeah, just don't put your ground there is the moral of the story. But this is the problem that's given me, so we'll just do it with the ground in that dumb place. So a bunch of voltage sources that are not touching the ground. So I have to make this big supernode that includes all of them. And then do a Kirchhoff's current law for that supernode. So I'll call this node V1, call this one V2, and call this one V3. So V2 over 4, right, plus V1 over 4, plus 1/2, plus V3 over 10, minus 1/2 is equal to 0. So multiply both sides by 20, get 5V2 plus 5V1 plus 2V3 is equal to 0. Cool. And then we have the relationship in the voltages between the different node voltages due to these voltage sources. So V1 minus V2 is equal to 3, and then V3 minus V2 is equal to 4. So put this in a matrix. 5, 5, 2, 1, minus 1, 0, 0, -1, 3. You thought I'd mess up that last line. I didn't mess up that last line. Take the determinant of that. So first minor, 5 times -1 minus 0. Second minor, -1 times 5 minus -2, so 7, which is equal to -12. Hopefully I didn't mess that up. The odds are not for me. I'll call this D1 to make it less confusing than last time. I now take the right sides and I plug them in. So 0, 3, 4, 5 -1 -1, 2, 0, 1. Take a determinant. Is -5 times this minor, which is 3 minus 0, so 3, plus 2 times this minor, which is -3, plus 4, which is 1, which is equal to -15 plus 2, which is equal to -13. Okay. Okay. I don't like seeing 13. Not because it's an unlucky number, it's because it isn't divisible by anything. It tends to make math messy. It's unlucky, but not in a superstitious way. It's unlucky, like, in a tangible way. Okay. D2. Okay, 5, 1, 0. 0, 3, 4, 2, 0, 1, to 5 times 3 plus 2 times 4, which is equal to 15 plus 8, which is 23, which is even worse number. And then D3, 5, 1, 0, 5 -1 -1, 0, 3, 4. So it's equal to 5 times -4 plus 3, so it's -1, -5 times 4 minus 0, which is 4. So that's -5, -20 more, so it's -25. That's a nicer number. So then V1 is equal to 13 twelfths, V2 is equal to 23 twelfths, and with a minus sign, and then V3 is equal to 25 twelfths. Let's see, does that check? So do V1 minus V2 equal 3? V1 minus V2 is 16 twelfths, so yes, it does equal 3. Does V3 minus V2 equal 4? V3 minus V2 is 25 twelfths plus 23 more twelfths, which is 48 twelfths, which is 4. That checks. Is 5, so 5V2 plus 5V1 plus 2V3 equal to 0. So, well, these are all 12s in the denominator, so just got to add the numerators up with weights of 5, 5, and 2. 65 minus 115. So 65 minus 115 is minus 50. Plus 50 is 0. These all check. I did it. They check. No stupid mistakes this time. Got it. V1, V2, and V3. Next example problem. So first I got to pick the ground. I'll pick it where most things are connected and is next to a voltage source, right? So right here. And then I gotta do my node equations. The only thing I have to do is one supernode here, right? So let's do the supernode. Let's name this VA and name this VB. So VA minus 6 over 5 plus VA over 40 plus VB over 20 minus, I believe that's supposed to be a 1 amp, even though it's written poorly, so it looks kind of like a 2, equals 0. And then I have my supernode, which is VA minus VB is equal to minus 12. This is a 2 by 2, which is nice. I'm going to multiply both sides of this by 40. So coefficients of VA, it would be 8 plus 1. So 9 VA. And then coefficients of VB, that's a 2, right? So plus 2 VB. And then we have this minus 6/5 minus 1. Both go to this side. So 6/5 plus 1 is equal to 11/5. And they got to multiply by 40. So that's 88. So look for an easy elimination. I think I have one. I can change this one into 2 VA plus 2 VB is equal to minus 24. Was minus. Eliminate down and get 11 VA is equal to minus 24 plus 88, which is equal to 64. So VA is equal to 64 over 11. VB is equal to that plus 12. So VB is equal to 64 over 11 plus 132 over 11, which is equal to 196 over 11. Okay, so I expect 64 over 11 minus 196 over 11, which is minus 132 over 11 is equal to 12. That checks. VA minus 6. This one is a bit, the other check is a bit longer. So 64 elevenths minus 6 is minus 2 elevenths over 5. So minus 2 over 55 plus VA over 40, which is, this is hard. Divide by 4. Divide by 8, right? So it's 8 over 55. Plus VB. 196 is divisible by 4, I believe. It's 36 plus 160, which is 40 plus 9, which is, well, 49. So plus 49 over 55. Minus 55 over 55 is equal to 0. So minus 57 plus 57, so that checks. So my work checks, and my VA is 64 over 11. My VB is 196 over 11. Last example problem. Dear. Let's see, how many nodes? I have 3 nodes. Call this one VA, call this one VB, call this one VC. Okay, write down my node equations. VA over 1 plus VA minus VC over 4 plus, just why am I writing plus here, is minus 2 is equal to 0. VB over why I said B and wrote A. VB over 2 plus VB minus VC over 1 plus 2 equals 0. VC minus VA over 4 plus VC minus VB over 1 plus 2ix, which is VB over 2, equals 0. So I'm going to clean these up a little bit. So the first equation, multiply both sides by 4. I get 5VA minus VC is equal to 8. Don't forget to multiply the right side by 4 like you tend to do. The second one, multiply both sides by 2. 3VB minus 2VC is equal to minus 4. Don't forget to multiply the right side by 2. And then this last one, these cancel. This cancels, so that cancels that, right? So I have another relationship that relates VC and VA. I better agree with this one. So multiplying both sides by 4. Oh dear. 5/4 VC minus 1/4 VA is equal to 0. What monstrosity have I just created? What did I do? What? This may be an interesting finale to this. It looks like I have two equations that disagree. What does this mean? Like, how do you solve that? Nope. I'm fine. I think I'm good. Okay. I don't know what I was up to there. 5VC minus VA is equal to 0. Sweet. Well, I get some. I got a little 2x2 here. That's easy to deal with. So 25 VC minus 5 VA is equal to 0. So 24 VC is equal to 8. I want black. Is equal to 8, which implies that VC is equal to 1/3. And if VC is equal to 1/3, then 3VB is equal to 2/3 minus 4. So VB is 2/3 minus 12/3 is minus 10/3 divided by 3 is minus 10/9. And VA is just 5VC, so VA is equal to 5/3. So let's see if that checks. 5/3 plus 5/3 minus 1/3 over 4, so 5/3 plus 1/3, which is 6/3, which is 2. Yeah, so the first equation checks. The second equation, minus 5/9 minus 5/9 plus 4/3 plus 2. So 4/3 plus 6/3 is 10/3. Oh dear, it's looking like the this middle equation here is not checking, which is silly. So let's see. Multiply both sides by 2. I get 3VB minus 2VC is equal to minus 4. And I used that to find VB. So minus 2/3. 2/3 minus... okay. 2/3 minus 12/3 is minus 10/3 minus 10/9. Why won't that check? Minus 5/9 plus VB minus VC. Oh. I messed up. I messed with the check. That could happen. Plus minus 10/9 minus 3/9 plus 18 ninths is equal to 0. Yep, that checks. Okay, that checks. And then the last one, VC minus VA. This is VC minus VA over 4 is minus 1/3. And then VC is a third, so it looks like that checks too. Okay. I didn't check it super thorough, but these should be the answers. Okay, if you made it this far into this was quite long. Hopefully you understood it. If you didn't, find somebody else and try to understand it from them. It's very important that you understand this. I don't care who you are. Everyone needs to know how to do node voltage. Facts. If I made a mistake, I won't ever hear the end of it. And that's about it. Yeah. Thanks for doing my old circuits homework from when I was a freshman in college with me. It's not exactly the same problems. I changed up the numbers so I wouldn't, rip off somebody. But that's basically what this turned out being, is like a show of someone doing their homework kind of live. Okay, I'm going to follow up on something that I brought up in some previous lecture that I made, and that is conservation of energy. So the sum over all elements in your circuit of voltage multiplied by current is equal to the sum over all elements of the current through each element multiplied by the voltage across that element, which is V on the plus side, the way the current is defined, minus V on the minus side, the way that the current is defined. So I define an arbitrary current through each element, and however I've defined that current, the power will be that current multiplied by the voltage. This is power dissipated, so for all these it's dissipated, such that the voltage is defined with whatever voltage is here is upstream of the current, and this voltage is downstream. Now every element will contact two nodes, and it has to contact two nodes. And if I count for all the nodes, I must have accounted for all the elements. So this is the sum over all nodes of the sum of all elements touching that node. I can't write. Of current coming out times that node voltage, or the current going in times minus that node voltage. So if I have two nodes, an element connecting them, and I define my current and my voltage up here, like so, the way your element direct interaction with each node will be either it's the plus terminal and the current's going out, or it's the minus terminal and the current's coming in. And because each element has a term for both nodes, here and here, for each node I need to sum over all of the elements coming in to touching that node, one or the other. Okay, so this equals this. Now I can then change the sign of this. Change the sign by just turning this I in into an I out. The signs will cancel. So this is the sum over all nodes, and for each of those nodes, all elements per node of the node voltage multiplied by current out. And by Kirchhoff's current law, that is 0. So the sum over the entire circuit of V multiplied by I, where I is defined according to voltage drop, for all of these, I goes from the plus to the minus, will add up to 0. So that should make more sense now. So that wraps this up. Again, reminding you that feedback mechanisms exist. And that's it. This was very important. The next one should be mesh current. And then so on. To conclude, I will slowly pan through each of the layers such that you can pause the video on any particular layer. I've tried to make this come out nice, it just doesn't.